This video is a tutorial for the installation and basic usage of the OxWearables Stepcount package, an open source tool for extracting step counts from raw wrist-based accelerometer data. The package was developed by the OxWearables team at the University of Oxford and is an easy-to-use and robustly validated research tool. The Stepcount package was trained on free-living, ground-truth annotated step data and utilizes a hybrid self-supervised learning algorithm to detect steps. A link to the validation study is provided in the video description below, and the labeled accelerometer data used to train the algorithm is also freely available. The Stepcount package can be found on our GitHub page at github.com/OxWearables/Stepcount. It can be used in Bash, Linux, or Windows. I'm going to use Windows today to show you how to install and run the system. If you don't have Python already installed on your computer, what we're going to do is go ahead and download Miniconda, which is a lightweight version of Anaconda, which holds a lot of data science tools, including Python, within the platform. So we're just going to click the Miniconda link right here and go down to the Windows Miniconda 3 Windows 64-bit installation. I'll click this. We're going to download the executable, open the installer here, and I'm just going to follow the recommended default settings. So I agree to this. This is just for me. I'm happy with all of this, and I'm going to go ahead and install the packages here. This might take a minute, but once we have this, we'll have everything we need ready to go to install Stepcount on our machine. All right, once the installation of Miniconda 3 is complete, so we're just going to click Next here. I'm going to uncheck these and hit Finish. From this point, what I'm going to do is to go into my Start menu and look for Anaconda Prompt. Now I have Anaconda Prompt from Anaconda 3 already installed on my computer, but what you'll have is Anaconda Prompt Miniconda 3. And we're going to go ahead and open that up. As you can see, our current working directory is in my own user folder, and that's probably what will come on your computer as well, c/users/whatever your Windows username is. You can change this location for installation if you'd like to, but in this case, this is fine for me. To install the Stepcount package, all I'm going to have to do is type pip install and Stepcount, and then hit enter. And what this is going to do now is going to install all the background Python packages that the Stepcount package needs to run its analysis. This will take a few minutes, and we'll come back once it's installed. Our installation is complete, and it's time to test out the package. In the video description below, we've provided a link where you can download a sample file from an Axivity AX3 device. What I'm going to do is just plug that link into my browser. One thing that you'll notice if you're familiar with Axivity devices, the file type for Axivity is a CWA file. In this case, we have sample.cwa.gz. That GZ is a compressed file, a compressed version of the CWA. The Stepcount algorithm can use compressed files or uncompressed CWA files. We can also use ActiGraph or GENEActiv files or any CSV file from an accelerometer, as long as it has columns that are labeled time, X, Y, and Z. I've moved the sample file from the downloads folder to our working directory here, the users/scott_s, so that we can easily access it when we're running a step detection algorithm. So from this point, we have our accelerometer file in the folder that we're working in. The only thing that we need to do is to type Stepcount, get it spelled right, Stepcount here, and then the name of the file. So in my case, it is sample.cwa.gz. And we hit enter, and it's going to go ahead and process that file. Okay, now that analysis is done, let's have a look at the output in the Anaconda prompt. First, you see wear time. This was a 7-day wear protocol for this participant. And you see that the participant wore the device for 5.8 days, or a little bit more than 5.5 days. The algorithm also does a calibration, so it'll give you the calibration error before and after calibration. And this binary 1 tells you that the calibration was past calibration test, that it was okay. Something else that you get here is the total number of steps for the total recording. In this case, the participant took 71,684 steps over a course of 734 minutes of total walking. Something else that the algorithm does is impute step counts during non-wear times. So if someone didn't wear the device, let's say from 1 to 2 o'clock on Wednesday, the algorithm will look at the other weekdays around that day and estimate the number of steps that participant took during that non-wear time. So you'll get the crude steps here, which is the true number of steps that the algorithm is counting, and adjusted steps, which is the result of the imputation. The package creates an outputs folder in your current working directory, and within that folder, you'll have individual folders named after each accelerometer file that was analyzed. In this case, our accelerometer file was called sample, and so we have a sample directory. You'll see several different types of CSV files here. We have daily step counts, daily walking time, hourly steps, hourly adjusted steps, and in this final CSV, sample underscore steps, we have steps at the 10-second epoch level for the entire course of the accelerometer file. And that's the file you'll want to use if you want to dig into cadence metric. And that's it. You now have a system in place to conduct free living validated step counts from your wrist-worn accelerometer data. We hope you find this tool useful, and do feel free to check out our biobank accelerometer analysis package, which uses the same framework, allowing you to conduct full physical activity analysis, including sleep and non-wear detection, cut point analysis, the integration of validated machine learning activity classification models, and a pipeline to train your own bespoke random forest classification models on your own data. Thanks again for watching, and good luck.